Hi, hello everyone. This is Dr. Chiranjeevi Manike, Professor and Head of Data Science and Cybersecurity Department, MLR Institute of Technology, Hyderabad. As part of data mining video lecture series, now we are going to discuss a Navy-based classification example. Previous lecture, we discussed about a Bayes theorem, how the Bayes theorem works. Now we are going to apply this Bayes theorem to solve a numerical example. So let us see what data set we are going to consider here and what are the features of that particular data set. So here the data tuples mainly are described by the attributes like age, income, student, credit rating, etc. in this data set mainly. So here this is a tuple, and this each tuple would be described using attributes called as age, income, student, credit rating, etc. And this data set has a class label attribute, that is Bayes computer. This is a class label attribute. Bayes computer has the two distinct values, namely yes and no. So let the C1 corresponding to the class Bayes computer be yes, and the C2 corresponding to the Bayes the computer. So this is by mistake it happened, I think. So computer that is equal to yes, and here the computer that equal to no. So let us see the full data set, and in this full data set we have 14 tuples in the data set. The tuple we wish to classify is, this is x, where x equal to age value youth, income is medium, student is yes, and credit rating is fair. So then we are going to predict the class label of this attribute by using a Navy-based classification. It is very simple classification. So once you understand the Navy-based theorem, and mainly the Navy-based theorem, that is probability of A given B equal to probability of B given A times probability of A over probability of B. So here we need to understand what are all these terms. This is a posterior probability, and these two are the prior probabilities, and this is also called as normalizing constant. So we have to calculate the probability of each class labels. So that is to accurately predict, or what is the probability, like suppose there are the different class labels. So what is the probability, like we have yes and no in this data set. So what is the probability of the class label x that is no, and what is the probability that the class label x is yes. So let us see how we are going to apply this Bayes theorem to solve to find out the probability, to find out the class label of this tuple x. So here, so we need to maximize, as we discussed in the previous lecture. So we need to maximize the probability of xi. Let me write the equation first. So probability of ci given x equal to probability of x given ci times probability of ci over probability of x. So we have to maximize. So here we have to maximize the probability of x because it is a constant. So we have to maximize this probability of x, probability of x given ci times probability of ci. This is a posterior probability and the class prior probabilities. So now this same formula we are going to use to calculate the probabilities. So it's very easy to understand this problem. So I just have to calculate the values. So let me write, like suppose, so for this, as I said, we need to maximize this probability of x given ci and probability of ci. What is I here? I would take the two values 1 and 2 because the class label, that is Bayes computer, has the two different unique values, yes and no. So that's why here I would take the two values. So then the prior probability of each class can be computed, this probability of Ci. So probability of Ci, that means probability of Ci, where I equal to, let us say, yes. So this I can write like probability of Bayes computer. Probability of a Bayes computer that equal to yes. This is a prior probability of the class label. So here the probability of a Bayes computer, yes. So we have the 14 tuples in this data set. How many tuples are with the class label yes? So there are 9 tuples in this data set out of 14, total 14 tuples. So if you would simplify this, then we'll get a value 0.643, etc. So then similarly, we would also calculate here the I value is 2, that means the second category, that is probability of Bayes computer equal to no. So that means here how many tuples with the class label under this are under the class label, how many are with the label no. So out of 14 there are 9 class labels with a yes, then remaining 5 class labels. So then that would be expressed as 5 out of 14. Then this is equal to some 0.357. I'm directly writing the values. You can also calculate it. So next, so we have to compute this is the prior probability, class prior probability. This part we have calculated. Now we have to calculate this part also, the probability of X given Ci. That is the posterior probabilities also need to be calculated. So let us take another slide here. So now let us calculate the posterior probabilities. So in this case, let me write it again, probability of X given Ci, where I equal to 1 and 2 values we will take. So now if so, then we are going to write the probability. I'll write a few directly, like probability of age equal to youth, probability of age equal to youth given Bayes computer that equal to yes. So similarly, probability of age equal to youth given Bayes computer equal to no. Okay, so this is for this age youth, and similarly there are probability of income that equal to medium. That is the tuple we have taken, right? The values, these are all the values. If you go back here, you can see the tuple age, we have to consider the youth, and the income we have to consider medium, and the student yes. So that's why here I'm going to calculate the posterior probabilities for each. So medium, so then the similarly like Bayes computer equal to yes, the same, the probability, this is same, and given the same here the values no. Similarly for the probability of, what is the next here, student, I think, yeah, student yes, student equal to yes given this Bayes computer yes, and one more probability, that is student yes, or student yes, given By's computer no. So we have to calculate this posterior probabilities. So then we have to apply this for the student and also the credit rating. I think we have the rating also, another attribute rating. So we will also write the probabilities. We have to calculate the probabilities for the, that is probability of rating is fair given the By's computer is yes, probability of rating equal to fair given the By's computer is no. So we have to calculate all these probabilities, posterior probabilities. So using these probabilities, so we would obtain, let me take, yeah. So we would obtain, that is the probability of X By's computer, that is yes. Okay, the probability of X given By's computer X. So that, as per the, if you would expand this form, so then it would be written as probability of age equal to youth given By's computer equal to yes. Okay, like the formula phi k equal to 1 to n p of xk given ci. Okay, so we are going to use this formula to calculate this. So times probability of income, what is the income category? Medium given By's computer yes, times probability of credit rating, that is fair credit underscore rating equal to fair given By's computer yes. Like we'll expand this and then we'll substitute the values like we have already calculated. The previous slide we have calculated this, all these probabilities. So once we plug all those values into this equation, so then we will get the value, let us say like 0.044 is the final value after plugging the values of these, all these probabilities into this equation, and the final value would be 0.44. So similarly we have to calculate, so this is equal to 0.044, and similarly we would calculate the probability, that is probability of X given By's computer that equal to no. Okay, so then the same, similarly we will calculate the probabilities of all this. So then we will get the value. So we know the class probability. So then let me write this value, probability of X given the By's computer, that is no. So that equal to 0.019. So to find the class Ci that maximizes this, so if you go back to the equation, that is probability of X given Ci times probability of Ci. So we have already calculated the class prior probabilities, and these conditional probabilities, the posterior probabilities are also calculated. So then we calculate the value, that is probability of X given By's computer is yes, equal to yes, times, okay, this one, and the class probability, that is probability of, So here I will remove this part. So probability of Bayes computer equal to yes. And similarly, another for the next class, that is probability of x given Bayes computer yes, no, no, and similarly, and the probability, another probability, that is Bayes computer is no. So then if you multiply these values, then we will get the first, I think, yeah. So let me write here 0.028 is the first value, that is probability of x given Bayes computer yes times probability of a Bayes computer yes. So then the second, for the second class, that is equal to 0.007, that is for this one. So then which is the highest probability? 0.027 is the highest probability. Therefore the naive Bayes classifier predicts that the class label of this, that is Bayes computer yes for the tuple x. So that is the way we solve this problem. The calculation part is very simple, but only the thing need to understand is this, all these posterior probabilities, prior probabilities. So if there are many attributes, then it would be little bit clumsy. So we have to write it clearly. So let us understand how the effective or these Bayesian classifiers. So various empirical studies of this classifier is in comparison to the decision trees, neural network classifiers have found it to be comparable in some domains. In theory, the Bayesian classifiers have a minimum error rate in comparison to the all other classifiers. However, whereas in practice, it's not always the case, that is inaccuracies in the assumptions made for its use, such as class conditional independence, because the computational power, the computational cost, that is would be more expensive, so they made an assumption that the class conditional independence. So that is the reason the lack of available probability data. So Bayesian classifiers are also useful in that they provide a theoretical justification for other classifiers that do not explicitly use the Bayes theorem. For example, under the certain assumptions, it can be shown that many neural network and curve fitting algorithms output the maximum posterior hypothesis. That is, maximum posterior hypothesis means probability of Ci given x. So this, that is for a class label Ci, the probability of Ci given x is maximum, and that is the maximum posterior hypothesis. So that's it. Thank you for watching. So next video we'll see the another classification approach.